Okay, so welcome everybody to the Urban Heat Island Effect Group, part of the NASA SEAS program. You'll be seeing the final presentations of our students for summer 2021. There we go. Okay, so our program consists of 6 high school students from around the United States. This was a completely virtual program this year. Normally the SEAS internships are face-to-face in Austin, Texas, but this year everything was virtual. So we here at the University of Toledo and the Globe Mission Earth program hosted this Urban Heat Island group. And the program was structured so that the students learned the following tools and then conducted their own independent research. And they learned how to collect surface temperature, air temperature, and clouds data from their immediate environments around their homes using the GLOBE program. And then they would export that data into ArcGIS Online and map it and analyze it along with other layers of data. And then also pull thermal satellite imagery and from the USGS Earth Explorer site, and then bring it into Multispec and QGIS for analysis. And they also utilize something called Lucidchart, which is a great tool for constructing a conceptual model so that they could visualize their research process. So we have 3 groups, 3 groups of 2 students each. And group 1, their project title is Measuring Impacts of Urban Heat Islands on Local Bodies of Water. Group 2 is projecting the urban heat island effect using historical weather patterns and land cover. And group 3 is the effects of lockdowns on air pollution and urban heat island effect. So just as an overall background, because this is the common thread throughout all of these projects, I just wanted to quickly go over what the urban heat island effect is. And it's the tendency of urban areas to have warmer temperatures than the surrounding more vegetated areas. And this is because of the amount of impermeable surfaces such as asphalt and concrete, which have a lower albedo, meaning that they absorb more of the sun's energy and don't reflect as much of it, whereas trees and vegetation actually reflect a higher amount of that energy. And so the urban areas re-radiate that heat, that absorbed energy as thermal energy in the afternoon and evenings. And additionally, urban activities such as air conditioner use and vehicle exhaust also contribute heat directly to the urban heat island effect. So we'll get going to the student projects, and the first project will be Kimi, Monforton, and Ray Trainer. That's measuring impacts of urban heat islands on local bodies of water. And then we'll move to group 2, which is Sam and Moneel, and group 3, which is Salma and Milton, and you can see their titles there. So I will stop share and allow Kimi or Ray to take over.
Okay, so our project was on measuring the effects that urban heat islands have on bodies of water. So we were interested in studying how the buildings can possibly raise water temperature. And so we did this, we collected field data from local bodies of water in Bozeman, Montana and McLean, Virginia. And we found out that our urban and suburban sites were 1 to 5 degrees Celsius warmer than the rural sites, and our findings demonstrated the negative effects that the urban heat islands can have, and also show us the need to mitigate rising water temperatures to protect watersheds.
So our research question was, how does the urban heat island effect impact the temperature of local bodies of water? We had a few reasons for asking this research question. Number 1, water bodies cool off cities in the summer, reducing the urban heat island effect. So we wondered if cities heat up water bodies in return. After all, that heat must go somewhere. Additionally, when it rains, urban infrastructure like concrete and asphalt heats up that runoff as it flows into storm drains and then into streams and lakes without being given a chance to soak into the ground and cool off. We also asked this question because when water heats up, it hurts the ecosystem. Hot water can hold less dissolved oxygen, and there are fewer organisms adapted to higher water temperatures, and it does benefit bacteria, which can increase their decompositional activity and create harmful chemicals in water bodies. Because of the factors we mentioned above, we expect that the temperature of local water bodies will be higher at urban sites impacted by that urban heat island effect than at rural ones. We looked at some previous studies to see what scientists has already discovered on this. Summers et al. In 2013 conducted a field study of 118 streams in North Carolina, half rural and half urban, and they found that urban streams were consistently warmer by about 1 degree Celsius than their rural counterparts. They also observed that after a storm, runoff from city infrastructure can raise stream temperature by 4 degrees Celsius in just 10 minutes. Another study was conducted by Briciu et al., who measured temperatures both upstream and downstream of Suceava city, Romania, and they found that the downstream temperatures were warmer by about 1 degree Celsius. They performed an analysis of covariance and determined that this was directly caused by the urban heat island effect. We hope to observe a similar effect.
So here's kind of a timeline of the steps we took to do our research. We first picked out our sites. We chose one urban site with a lot of infrastructure and minimal vegetation, one rural site, which had a lot of vegetation and minimal infrastructure, and then we chose a suburban site, which kind of had a balance of both. We then used a software called Multispect, where we got satellite imagery of our sites. And then we also did supervised classification, where we were able to categorize the surrounding areas of our sites to confirm whether or not they were really rural or urban sites. And then we collected field data. So we got air, surface, and water data. And then we did that kind of following the GLOBE protocols. And then this was all done as close to solar noon as possible. And then we measured each site within 20 minutes to an hour apart. And then the last thing we did was analyze data through various tests to kind of come up with our conclusions. So here's just a map showing where our sites are located. And then it also shows the urban heat island effect with those yellow and red dots showing where there's more heat and activity and infrastructure.
On this slide, you can see a map of Washington, D.C., my local area. That anatomically correct heart shape in the center is D.C. itself. The sites are represented by the pins. Great Falls National Park is rural, Roosevelt Island semi-urban, and National is urban. On the next slide, here we have some satellite imagery of my urban location. In the top left is an image of the site taken from ArcGIS. You can see National Airport in the top and the data site pinned in blue. In the bottom left is an image in false color taken from Landsat 7. This is a 16 square kilometer area directly surrounding the site. Vegetation shows up as red in a false color image and buildings in white. We used a software called Multispect to classify the land cover in this false color image, and the results are in the top right. It's about a quarter vegetation and almost half impervious surfaces. On the next slide, this is my semi-urban site. Theodore Roosevelt Island is a popular hiking destination that's very close to the city. As you can see, it's closer to a third vegetation in that 16 kilometer square land cover, but it actually has a few more impervious surfaces than Dangerfield Island even. Great Falls National Park is my rural site. You can see that the ground cover is almost 3/4 vegetation.
Okay, so here's the map showing the Montana sites and then the urban heat island activity with all the yellow and orange coloring. Here's my urban site, which is a pond right in the center of my town's university. And then the supervised classification shows how much impervious surfaces are and how much vegetation there is. Here's my suburban site, which is a pond called Valley West that has more buildings, or less buildings and more vegetation than my urban site. And then here's my rural site, which is a pond called Elk Grove in a very secluded neighborhood with a lot of vegetation and almost no infrastructure surrounding it. And then here are just photos of us, of our sites and us collecting data.
Okay, so this is a graph of the water temperature over time that I collected in McLean. And you can see that the rural site, which is in blue, is consistently colder than the urban site, which is in red, and slightly colder than the semi-urban site, which is in yellow. We performed statistical analysis and did not get significant ANOVA results, so we conducted further testing. A t-test between the rural site and the urban site found that the warmer urban temperatures were almost on the threshold of significance. You can see a little bit of rainfall anomaly on July 18th, when it rained approximately 0.15 inches. As you can see, the temperature dropped very little in the urban and semi-urban sites, but it dropped a lot in the rural site after the rain. We hypothesize that this is because of heated runoff from the city infrastructure, which we described earlier in the literature review. This confirms our hypothesis that urban heat island effect warms water via runoff. You can see this effect again to a lesser degree on July 22nd, when there was a trace amount of rain.
Here we also graphed the water temperature over time in Bozeman, Montana, and as you can see, the ANOVA test came back statistically significant, and then almost all the t-tests we did were also statistically significant. And you can see that the rural temperatures were constantly colder than the semi-urban and urban sites. Here we also graph the surface and air temperatures of our sites, and although there wasn't any statistical significance, you can still see that there are many times where the rural sites were the coldest. So in both areas, we saw a very big difference with water temperatures and even some differences with surface and air temperatures. And so we saw that also the rainfall worsened the urban heat island effect on the Potomac River. So yeah, overall, our hypothesis was supported by the data, and that just shows how the urban heat island effect causes temperatures to rise in bodies of water.
We have a few next steps that could further the conclusion of this project. First off, we can improve our methods. When we measured our data, we couldn't successfully control for measurement time or total water body depth. These could have been confounding variables, so studies that controlled these would be more accurate. Any further studies should also be conducted over a longer period of time. We were limited by the length of our internship, but a longitudinal study would collect data on the climate of the area, rather than data that could be influenced by short-term weather patterns. Another interesting investigation would be to use our observation that the urban heat island affects watersheds and determine how that affects the health of aquatic ecosystems. These observations could be useful to decision makers in government and ecology. Lastly, another idea our group had was using machine learning to predict the extent of the urban heat island effect. Not only could this help future field studies of site selection, but a machine learning model could add to the significance of field data like ours in evaluating ecosystem health. You'll hear more about that in the next section of our presentation. For now, though, thank you for listening, and here are references.
Hi, I'm Srivatsan.
And I'm Moneel Patel. And our objective was to project the urban heat island effect using historical weather patterns and land cover. Here's an example of our abstract if you'd like to see more information about us.
Our research question was about how developed land cover and weather trends can be used to forecast the urban heat island effect. Timely, accurate predictions of future conditions can prepare scientists and communities to take greener initiatives and to adapt their lifestyle to preserve the earth. We attempted to answer this question in a couple of different ways.
An urban heat island is a metropolitan area with higher air and surface temperatures than surrounding areas. The urban heat island effect is a relative measure of urban heat islands. We chose to study the greater Austin region in Texas, but don't worry, because Sam lives in California, I made sure to give her a hard time for not living in heat like we do down here in the Lone Star States.
The first technique in our study was using machine learning to find correlations between some factors that are closely linked to the urban heat island effect. Our factors were air and surface temperature, relative humidity, soil moisture, and population growth. So there's a lot going on the screen, but let's just focus on the three main stages of part one, which is the computational modeling section. So the first stage is data collection. We use the Globe Advanced Data Access Tool and Visualization System, as well as the UN Population Prospects Database and the US Geological Survey as input data sources. The second stage was data analysis, which is where we cleaned the data up and dealt with any inconsistencies. And the third stage was identifying correlations, which is super important to be able to make predictions. Like if we know the relationship between multiple factors, we can use those to fill in gaps in data. For example, consider if we're testing our model and having it predict the air temperature in, say, 2015, but we don't know that value. Knowing the surface temperature and humidity at that time will help us fill in the gaps and find the air temperature in that at that time in that region. After cleaning up and plotting the data, we noticed a clear upward trend. This validated the urban heat island effect. We used that data to build a Keras sequential model, which is a type of machine learning neural network model. This is the correlation stage of the process where we wanted to find the relationship between different factors through correlation coefficients. Sequential models use a stack of layers. In deep learning, a layer is a container that receives weighted input, transforms it using a set of nonlinear functions, and then passes that output of that layer to the next. So think about kind of having a stack of blocks, and you're passing a string through each of the blocks, and every time you're making a modification to that string and passing that new modified string into the next block. That's kind of how it works with these layers. We downloaded the data by manually importing CSV files and cleaned it up using the NumPy and Pandas software libraries. These libraries helped us manipulate data frames and plot and visualize data. If you tend to work with larger scale data or you're familiar with the Python programming language, I highly recommend NumPy and Pandas. We use those correlations from the sequential model to make preliminary predictions about the present, and then we compared them to actual data points. Take a look at the top right corner, and as you can see, those predictions got pretty close to the actual values. However, they still need to be trained and tested further on more extensive data sets.
The second simultaneous part of our project was studying future land cover land use. For our purposes, we use QGIS, an open source satellite imagery software, and in order to predict future land changes, we use the Modules for Land Use Change Simulations plugin developed by AirAsia Survey and NextGIS. The process is quite complex, but at a base level, it takes rasters of land use categories from 2 different time periods and rasters of explanatory variables, which in our case, we chose to use distance from road and distance from inland water bodies. The data then runs through evaluation correlation, which in our case, we use Kramer's coefficient, which measures the strength of association between the different land cover classifications. It then creates a transitional matrix and calculates the individual pixels and area changes between the classifications, which then runs into an artificial neural network-based transition potential model, finding confidence in probabilities of certain pixels changing. Finally, and most importantly, the data runs through a cellular automata simulation with sets of pixels being classified into neighborhoods and predictions based on these clusters. These are the original inputs sourced from Diva GIS. We then rasterized and used the Euclidean distance function in ArcGIS for our inputs. For some context, rasterization is taking scene geometry and converting it into pixels for display on screen. For reference, we've added some maps prior to our simulation, sourced from the multi-resolution land characteristics consortium. And as we can see, the trends in 2001, we can clearly see the difference in urban sprawl between these years. Right here, 2016 is where we put our initial raster. 2019 was our final raster. And from these 2 maps, along with our earlier distance from maps, we came up with a 2022 predicted output map.
So we had part 1, which is computational modeling using primarily numerical data. And then we had part 2, which was using satellite image analysis. And looking at both models, we can see an increase in factors that contribute to rapid increases in the urban heat island effect. Although we can't really observe a direct causation, we speculate that there is a correlation between land cover land use and air and surface temperature in the Austin City region.
There are many possible uses for our finding, but the one we thought best fit was if it were to be used by local city planners in Austin in order to pass legislation to promote green spaces to counteract the urban heat island effect, which would in turn decrease energy consumption due to air conditioning requirements.
And with that, these are our sources, and I'll hand it off to Salma and Milton to talk about the relationship between lockdowns and the urban heat island effect.
Hello, my name is Salma Eldeeb.
And my name is Milton Nguyen.
And our project is the effects of lockdowns on air pollution and the urban heat island effect. So a quick synopsis of our project is that we focused on the urban heat island effect, which is a phenomena that occurs in many large cities, specifically in New York City. Many different factors fuel it, but we wanted to focus on vehicle usage mostly. We also took a look at air pollution in New York City. So the stay-at-home order was issued in New York City, and during that, vehicle usage decreased greatly, and that allowed for a decrease of air pollution as well as surface temperature, which was shown in thermal maps. So our research question was, how did the lockdowns caused by the COVID-19 pandemic impact air pollution and the urban heat island effect through the lens of vehicle usage in New York City? And we hypothesized that it would have caused decreased air pollution and urban heat island effect in New York City because of the decreased vehicle usage due to the stay-at-home order placed for quarantine.
So vehicle usage plays a role in the urban heat island effect since vehicles themselves can emit heat. A great way to track vehicle usage is by tracking particulate matter, specifically PM 2.5, since vehicles are able to emit PM 2.5 within their car exhaust.
And the areas of study that we mainly focused on were Central Park and Times Square. So we used multi-spec to do a supervised classification of both areas, and we saw that Central Park had 85% vegetation, 10% water, 5% buildings, while Times Square was 2% vegetation only and 98% buildings. So there was a stark difference in the landscape. We also chose those two areas because of the amount of purple air data in the purple air sensors that were nearby, which are a network of sensors around the world that collect particulate matter data. And our methodology started out with a research question, and then we chose our location and those specific parts, and also our time frame, which is before, during, and after COVID. We looked at a timeline of COVID-19 in New York City, and we chose the week that was in the middle of the start and the end of the stay-at-home order issued. And then we did the year before and the year after to compare. And some of the tools that we used were QGIS and Purple Air. So QGIS, we used Landsat 8 data to calculate those surface temperatures and present it via maps. And for Purple Air, we downloaded the PM 2.5 data and we created comparative line graphs.
So right here, we see the results from the PM 2.5 data from Purple Air, specifically for our Times Square sensor. We have averages for our time frame of interest by year. So on the right, we can see that 2020 has the lowest PM 2.5 value as compared to 2019 through 2021. And this indicates the lower vehicle usage rates. This right here shows the same exact data, but graphically depicted. The solid lines show each data point on a daily level, and then the dashed lines show that weekly average. This right here shows our sensor data from our Central Park sensor. Once again, we see that trend where 2020 has the lowest PM 2.5 data value, suggesting there was the least amount of car usage. And once again, right here, we have the same graphically depicted data showing that same low vehicular usage trend.
So also we use QGIS to create these thermal maps. So in these maps, the darker the red is the hotter the temperature, and the lighter the red is the cooler the temperature. So we have 2019 and 2020 depicted here, and you can see that 2019 does have a darker red compared to 2020, meaning it has hotter surface temperatures. You can also see the stark difference between Central Park and Times Square, where Central Park is a lot lighter, meaning it's a lot cooler. And 2020 was that during COVID time area, so you could see that during the stay-at-home order, surface temperatures cooled down compared to beforehand. And this is the 2021 map. However, it is a little unclear due to the cloud coverage found.
So for our study, we had a few limitations. So first off, there were no purple air sensors directly within our areas of interest, those being Times Square and Central Park. So we used sensors found a bit outside of each area of interest. Additionally, some limitations were that the data for the surface temperature in 2021 was unclear due to cloud coverage, and also no data during nearby dates was found for that either. And also many factors play a role in the urban heat island effect, so not only vehicle usage, so stating causation regarding the lockdowns may not be feasible. And for the discussion, so decreased vehicle usage from quarantine really inspired this research into the urban heat island effect. And this research can be further developed by looking into each factor that contributes to the UHIE. And certain environmental policies in urban planning could benefit from this research, since it would allow a better understanding in how to mitigate the urban heat island's negative effects.
So in conclusion, this was a research question again. And we found that particulate matter from the cars decreased greatly, but it was shown to rebound after those lockdowns were lifted. And surface temperatures were also shown to decrease during the lockdown. However, since that limitation regarding the 2021 data, we can't state what happened after the lockdowns were lifted. And we also saw that the difference in temperature between Times Square and Central Park was significant, with Central Park being a lot cooler. And overall, the air pollution in our area did decrease and then increase, like we said before. Lastly, more research can be done regarding the benefits of decreased vehicle usage in New York City, specifically regarding the air pollution and the urban heat island effect. And here were some of the references that we used in our project. Thank you.
So I want to take this opportunity to say personally how amazed I have been by all of our students in this process and how adaptive that they've been to working with one another, despite the fact that they're completely separated from each other physically. And so their collaborations have been done totally virtually, and they've executed these amazing projects. using their own video conferencing software to meet one another and sharing documents and files through Google Drive. And I'm just absolutely blown away by each of them. And you can see here that, you know, this, just like any complex experience like this, is full of great things and then also full of some challenges, which nobody actually added challenges. So highlights of working with the experience, some of them said, working with professionals in the field meant I could not only learn about the urban heat island effect, but about how scientific research is conducted in the real world. Thank you, Ray. Working in Cs allowed me to explore more branches of science that aren't afforded in my high school. Well, that's pretty cool. Thanks, Kimi. This program gave me a great and unique opportunity to learn about the urban heat island effect through an interactive research project rather than passive means. That's pretty cool, Milton. This experience allowed me to learn new platforms and data collection methods in an extremely interesting field, all while being provided with the opportunity to meet students and professionals interested in the same subjects. Awesome, Salma. And although the internship was quite difficult, it was very rewarding, and I am just so grateful for the opportunity to work with our mentors. And I will count that as a challenge, even though no one added it there. So once again, thank you everybody for watching our Urban Heat Island Effect group presentations. And we want to thank the NASA SEAS program for hosting this. And if you're interested, check out Globe Mission Earth for more about the Globe program. Thank you.